Section 7.3 is going to discuss arithmetic and geometric sequences. So we're going to have to learn a few formulas here. Get that screen out of the way. Maybe. Alright, there we go. So an arithmetic sequence is a sequence where you can find a common difference between each successive term. And there's a formula for an arithmetic sequence. There's several formulas, but the one we're going to use most often is a sub n equals a sub 1, which means the first term, plus the common difference d times n minus 1, the quantity n minus 1. And then there's a geometric sequence as well, and you would use a geometric sequence if you notice you have a common ratio. Oops, ratio from each term. And when we used to teach this to little Algebra 2 kids, which I don't think we taught the last few years, common difference for arithmetic sequences mean you were adding, and then sometimes they viewed it as a subtracting a common term, and common ratio meant that we were multiplying, and some kids view that as division, depending on what the R is. The geometric sequence formula is a sub n equals a sub 1 times, and then whatever the common ratio is, to the n minus 1 power. So moving on, we have to decide whether or not these are arithmetic or geometric sequences. So you kind of just look at the pattern, and I see -7 to -2 to 3 to 8. I notice that we're adding 5 each time, so that means it's an arithmetic sequence. And since I identified that we're adding 5 each time, that's the common difference. And obviously the first term is the -7. So using my formula, which says a sub 1, which is -7, plus the common difference times n minus 1. Now that's an okay version of the formula for working purposes, but generally they want you to simplify this. So we're going to distribute the 5 and then collect like terms. So my general term, my formula for this arithmetic sequence is 5n minus 12. Here on letter B, I notice that we are multiplying by 5 to get from one term to the next. So that means that this is a geometric sequence. And the multiplying by 5 means that my common ratio is a 5. And my first term I can see is a 1. So using my geometric formula, it says take your first term times your common ratio, which is 5, to the n minus 1 power. And what I kind of like about geometric sequences is you can't simplify them at all. The only thing you can kind of do to this one to clean it up, the coefficient of 1 is not necessary. So it's really just 5 to the n minus 1 power. If I look at letter C, looks to me like a lot of kids say, oh, they're dividing by a -2 each time, which is kind of true, but when we look at common ratios, we are only discussing them in terms of multiplying by something. So instead of dividing by a 2, we can say that we're multiplying by a -1/2 each time. -2 times a -1/2 gives me a +1, and so on and so on. So there's my common ratio. My first term is a 4. So my formula is 4 times -1/2, and then to the n minus 1 power. And there's no simplifying you can do on that formula. In letter D, it looks like a lot of little kids say they're subtracting 3 each time, but remember, the common difference has to be in terms of adding something. So you could think of it as subtracting for now, but when I go to the formula, a sub n equals, my first term is a 10, and then we're going to say it's plus a -3, which we know is really subtract 3, times n minus 1. So if I distribute the -3, get -3n plus 3. So my general term, or my formula, is -3n plus 13. Okay, now I'm going to tell you that we have a sequence, and it didn't say in the directions, but this is an arithmetic sequence. And I give you the first term, and then I give you the 10th term, and I want you to find first the common difference, and then eventually find the 50th term. Now, some kids think they should just, write out the pattern forever and ever and ever, and that's not a terrible way to do it. It's just not a real efficient way to do it. I'm going to write the general form right here, a sub 1 plus d to the n minus times n minus 1 power. Times the n minus 1 factor, excuse me. This formula is for the nth term, so I could use it for any part of the term of the sequence that I want. Since they gave me the 10th term, and I know it's 30, I'm actually going to use that clue in the formula. So I'm going to say the 30 is going to go right here in the a sub n for the nth term. So I'm referring to the 30th term of the sequence is equal to the first term, which is 3, plus, I do not know the common difference, so we're going to leave it as a variable. And then the n, because I used the 30th term of the, or sorry, the 10th term of the sequence, the n I'm using here is a 10, minus 1, of course. Some people like to think of this more logically, and they say to get from 1 to 10, you had to do 9 additions, 9 jumps, if you will. And that's how a lot of people complete these problems. So what I really have is 30 equals 3 plus 9 jumps. I'm going to subtract the 3, 27 equals 9d. And my common difference I now see is a 3. So if I go back to my general form, and remember that a sub 10 equals 30, I just used to find the common difference. I'm not going to use it anymore. This time I want to know the a sub 50. So the 50th term is my first term, plus I just found my common difference of 3, and then if I'm trying to find the 50th term, I can put a 50 in for n. And then I'm just going to compute that. So let's see, 3 times 49, okay, I think that comes out to 150. So the 50th term of this sequence is 150. Similarly on part B, I know that I have a geometric because it talks to me about the common ratio r. So, using my problem, let's see here. Oh, I did this wrong originally. Haha. I'm just looking at my key and realizing I'm silly. So, I'm going to use this 10th term clue to figure out my common ratio first. So, the common ratio, the formula is a sub 1 times common ratio to the n minus 1 power. So, the 10th term is a 4. I know my a sub 1 is a 1. I have no idea what my common ratio is, but since it's the 10th power, this would be like 10 minus 1, or the 9th power. Now this is kind of crazy. I get 4 equals r to the 9th power. Gross. I would either take the 9th root of that, or I could take it to the 1/9 power. That is a really disgusting problem. Yuck. I don't think that's anything pretty. So my common ratio is 4 to the 1/9 power. Yuck. So finding the 17th term of this geometric sequence would be taking my first term, which is a 1, I'm not even going to write it, and then 4 to the 1/9 power to the n minus 1. Now since I want the 17th term, it's a 17 minus 1 power. Oh my goodness, this is terrible. 17 minus 1 is 16. So I have 4 to the 1/9 times 16 is really 16/9. And I don't really know what this number comes out to, so we're just going to leave it as that. I don't think I wanted that problem to look that disgusting, so not bad. Alright, on the back of these notes, it's 7.3 part 2, and now we're going to talk about different formulas for arithmetic series, and then we're going to see a finite series and also an infinite series. We're not going to, we will talk about infinite geometric series at the end of this. So formula number 1, if you think you have enough information to use this formula, then it's the right one. So if you know the number of terms, it's n minus 2 times 2 times the first term, or double the first term, plus n minus 1 quantity times the common difference. So basically, if you have your common difference, or your first term, or you know the number of terms, that's when you use that formula. A different formula that'll arrive at the same sort of answer you can use if you know other things. For instance, if you know the first and last number. And this is actually a very famous formula. I forget which mathematician, but some smarty pants way back in the day was harassing his math teacher, and his math teacher needed to give him a really difficult problem in like the 3rd grade, and he told him to add up all the numbers 1 to 100, and he of course thought that was too tedious, so he came up with a shortcut, and he realized that if he added the first and last number, 1 and 100, and then if he added the second number and the second to last number, 2 and 99, each time it gave him 101, and then he realized how many pairings of those he had, and actually this is the formula that he came up with as a little baby 3rd grader. So, number 3. Find the sum of the first 26 terms of an arithmetic series if your first term is -7 and your common difference is 3. Now the other thing I notice is they only want the first 26 terms, so this is a finite series, and my n is a 26. So I'm going to use the first formula that they gave me, which says n over 2 times 2 or double the first term plus n minus 1, so I know that's 25, but I'll just write it out for now, times the common difference of 3. And I'm just going to crank that in my calculator, because there's no sense in racking my brain, and it comes out to 793. Now, number 4, they want the sum of all odd numbers between 51 and 99 inclusive. Now, a couple of different ways to realize this answer. I know I have my first and my last number, and the other thing we need to kind of figure out is how many numbers do I really have. So, what some kids do is they just can kind of come up with a smaller problem and realize that there's 25 numbers listed there. But if you can't figure that out, we can do it, this will be an arithmetic sequence, so we can set up a sub n as the 99, and then my first term plus, now everyone gets confused here, but a common difference if you're counting by odd numbers is you're jumping over every other one, so you're counting by 2's, and then I think we just decided that we didn't know the n. So we can solve this problem for n. So I'm going to subtract 51, distribute actually I'm just going to divide by 2. So I get 24 equals n minus 1, so n equals 25. So now I know there's 25 numbers in the list, and now I can use that second formula for the sum of the finite series, where it says n over 2 times the first number plus the last number. And when I do that on my calculator, I get 1875. I kind of like that. Okay, now if we have a finite, oh, P.S. There was not, I spoke incorrectly earlier, there is no infinite arithmetic series, because if you tried to add an infinite arithmetic series, you would be adding for the rest of your life, because it does not converge or diverge, or whichever one it's called. So geometric sequences, or series, however, will, I believe the term is converge, if the absolute value of the r is less than 1. So you have a common ratio that's smaller than 1. And the formula for, oh, I'm speaking incorrectly again. This first section is referring to finite geometric sequences. So, excuse me, the finite geometric sequence formula is your first term minus your first term times the ratio to the nth power, kind of weird, and then divided by 1 minus r. And the other formula we could possibly use looks really similar at first. It is the first term minus the common ratio times the last term divided by, again, 1 minus r. And these are all assuming that your ratio, common ratio, is not 1, which means it wouldn't be geometric anyways. So depending on what you have, you might want to use one formula or the other. So this first example, find the sum of the first 20 terms of the geometric series. So I'm going to use the first formula because that's the information I have. So that'll be first term is 1 minus my first term again, 1, times my common ratio to the nth power would be the 20th power, over 1 minus the common ratio of 2. So typing that on my calculator, it's big. It's 1,048,575. Number 6, find the sum of the first 14 terms of the geometric sequence, or series, excuse me, given this information. So same formula. It's kind of a boring formula. Just be careful how you type it in. 1/64 minus 1/64 times negative 2 to the 14th power. Make sure you either type that in one step and then hit enter, or use parentheses, and then 1 minus the negative 2. So on my calculator, that comes out kind of gross, negative 85.33. Now let's talk about infinite geometric series. So we're finding this series here, and as we can see easily, the common ratio is that we're being multiplied by a 1/3 each time. It's infinite, so you're not going to be using any n's in this problem. But the sum of an infinite geometric sequence is your first term, a sub 1, divided by 1 minus r. And this is what I was babbling about earlier, where the absolute value of r must be less than 1 for it to converge. So, using my formula, first term is a 3, I can see, and then 1 minus 1/3. And just use parentheses if you're doing it in one step on your calculator, and we get an answer of 9/2. And then number 8, we're going to represent the repeating decimal of 0.45 as a quotient of two integers. Now there's a really easy shortcut, but what I want you to realize is 0.45 repeating is 0.45 plus 0.0045 plus 0.000045, and so on and so on and so on. So what's happening here is every term you're multiplying the 0.45 by 1/100th. That's how you're moving 2 decimal places over. And if I use my formula, my first term we decided was a 0.45, and then 1 minus the common ratio. Now I'm going to change 1/100th to 0.01 for my typing purposes. If I did that on the calculator, it came out to 45/99 at first, and then when I hit math enter enter, if I don't feel like reducing it in my head, I get a 5/11.